We're not actually going to prove this. I'm just going to give you a cautionary picture. The perturbation h that we select really does have to be small. If you take 2 points z and w in your star domain, then you don't need to have the triangle spanned by z star, z, and w fully contained in D. So here's a picture of the star domain. Here's a star center. Here's one point. Here's another point. And what is the triangle spanned by these 3 points? Well, it's this triangle. And we see some of this triangle does lie in our star domain, the part shaded in blue, but then there's that white part with the dashed line that lies outside the star domain. The problem is that relative to one of the circles, the other circle is too far away. So we can only have this triangle contained in D if the perturbation is sufficiently small. But we're doing analysis in calculus, and we only ever care about small quantities anyway when we take limits. Okay, so who really cares about star domains and triangles? Why are we spending all this time learning this geometry and these technical set theoretic definitions? Here is a lemma that's going to help us. Suppose that F is continuous on the star domain D, and let Z star be a star center. Suppose that for each point Z and D, if H is a complex number small enough such that the triangle spanned by Z star, Z, and Z plus H is contained in D, and that's always going to happen by the previous lemma if H is small enough. Suppose that if this triangle is contained in D, then the integral over the triangular path spanned by Z star, Z, and Z plus H of F is equal to 0. In other words, the integral of F around the triangle with edges Z star, Z, and Z plus H is equal to 0. Suppose this happens. Then F has an antiderivative on D. So all of a sudden, we have a rather technical but very explicit condition that guarantees that our function f has an antiderivative. It just has to integrate to 0 around all sufficiently small triangles with one edge on the star domain. So how can we prove the existence of an antiderivative? Let's do what we always want to do. Let's define the antiderivative to be the integral over a line segment. So we'll define capital F of z to be the integral over the line segment from z star to z of f. Now this is a well-defined function. Here's why. The line segment from z star to z is contained in D for all points z and D. And why is that? Because D is a star domain and z star is a star center. So I have no worries about whether or not this integral is going to exist. And unlike in the independence of path theorem, I'm not choosing some arbitrary path connecting z star to z, I'm choosing the line segment. So there are no well-definedness issues in play here. Now let's calculate, as we always do, big F of z plus h minus big F of z. That's the numerator of our difference quotient for the derivative. So this is the integral over z star to z plus h of f minus the integral over z star to z of f. And so what does this thing equal? Well, hopefully it equals something that we can control very nicely when we divide by h and take a limit. Instead, look at the 3 points involved in this integral, z star, z, and z plus h. That is, again, big F of z plus h minus big F of z is the integral over the line segment from z star to z plus h minus the integral over the line segment from z star to z. So here in dashed blue, that could be the star domain. I've drawn it like a ball just for convenience's sake here. Z star down the bottom there, that's the star center. I am going from z star to z plus h, one line segment there, and I'm going from z star to z, another line segment there. It looks like in the integrals above, the 2 line segments there really are just 2 sides of a triangle. And I know what f does when I integrate it over the triangle sketched here. Who cares about star domains and triangles, you ask? We care about star domains and triangles, I tell you. So what do we know? 0 is equal to the integral of f over the triangular path spanned by z star, z, and z plus h. And let's just write out what that triangular path is. That's the line segment from z star to z, composed with the line segment from z to z plus h, composed with the line segment from z plus h to z star. So I have the integral over a composition of three curves. That's the sum of the integrals over each of the curves individually. So I'll integrate over z star to z plus h, then z star to z, then z to z plus h, then z plus h to z star. So integral over a composition of three curves is the sum of three different integrals. And let's rearrange this equality a little bit, because I have three integrals adding up to equal 0. That tells me now that the integral over z star to z plus the integral over z to z plus h is really minus the integral from z plus h to z star. Now let's flip that around. I have minus the integral from z plus h to z star. That's also the integral from z star to z plus h, because I'm taking minus of an integral equals the integral over the reverse curve. Okay, so f of z plus h minus f of z, my putative antiderivative, is the integral from z star to z plus h minus the integral from z star to z. And I know now what this integral from z star to z is. So this becomes the integral from z star to z plus the integral from z to z plus h minus the integral from z star to z. And so I'm left with the integral from z to z plus h. Okay, why does that do me any good? Because all of this is telling me now that the limit as h goes to 0 of f of z plus h minus f of z divided by h is really the limit as h goes to 0 of 1 over h times the integral from z to z plus h of f. And that is a very special limit that we stated earlier. We know that's equal to f of z. So the limit of the difference quotient of big F is equal to f of z, and that tells us everything we wanted to know, that big F prime of z is equal to little f of z. This calculation on this slide is intense, and just looking at it now in full makes my eyes go a little glazed over and dizzy. But understanding how this calculation works, how you do the algebra of the integrals, how you rearrange some integral identities, how you use something like minus the integral over a curve is equal to the integral over the reverse curve, these are fundamental techniques for working with line integrals and complex calculus. And so I urge you to go back over this calculation, hit pause, rewind the video, and watch it again and work through it again until you understand it. So what have we done here? What are some conditions that will guarantee that f will integrate to 0 around triangles? In other words, if you have a star domain D with star center z star, and if f is continuous on D, do we need something else? What else could we possibly assume or impose to guarantee this integral condition that the integral of f over the triangular path spanned by z star z and z plus h is equal to 0 for all z and d and all complex h small? If we know the integral over the triangular path is equal to 0, then we know that f has an antiderivative by our explicit and lengthy construction on the previous slide. But what else out there exists in the mathematical universe that will force the integral of f over triangles like this to be equal to 0? Because nothing I said in the previous lemma told us that. I just started out assuming that the integral over the triangle was 0. Here is the answer. We call it the Cauchy-Goursat-Pringsheim theorem. Let f be holomorphic on some open set D, and let z1, z2, and z3 be points in D such that the triangle spanned by z1, z2, and z3 is contained in D. Then the integral of f over the triangular path spanned by z1, z2, and z3 is equal to 0. Here in this Cauchy-Goursat-Pringsheim theorem, the set D does not have to be a star domain, it just has to be open. And the points z1, z2, and z3, they don't have to be star centers or close to each other like in the previous lemma. There's have to be 3 points, such that the triangle spanned by these 3 points is contained in D. And if f is holomorphic on this open set D, pretty big assumption, certainly stronger than just continuity. If f is holomorphic, then the integral of f over this triangle will be equal to 0. So this answers our question of what else? What else do we need to guarantee that the integral of f over triangles with suitably nice vertices is equal to 0? Holomorphic. If f is holomorphic, the integral of f over triangles is 0, and antiderivatives will exist.